Hi everyone, I'm Zhou from Communication University of China, and my collaborators are Delong Chen from Hong Kong University of Science and Technology and Yudong Chen from Communication University of China. And my title is Towards Joint Modeling of Dialogue Response and Speech Synthesis based on Large Language Models. So, as we are developing more advanced AI systems, such as a large language model-based chatbots like ChatGPT and GPT-4, we also hope to establish natural, seamless, and efficient communication between humans and AI systems. In addition to typing and reading through the screen, the speech channel represents a valuable alternative for interpersonal exchange, given its convenience and capacity to convey richer information than text alone. Recently, researchers from both academia and the industry have made successful attempts to concatenate AI chatbots with off-the-shelf text-to-speech modules, respectively. Applications include Siri and Alexa. However, the expressivity and interactivity of speech responses synthesized by these two-stage cascaded models are heavily limited. Although the TTS today is already very human-like and the Morse score is very high, it cannot react to the speech or text of the users. There's no change of the intonation and emotion of the generated speech. No matter how humanoid the sound is, the tone is very monotonous without any change. We think the reasons are twofold. Firstly, TTS modules are usually based on small language models like BERT, which have limited capacity for understanding complex dialogue context. And secondly, the dialogue response generation module and the TTS work independently. During speech synthesizing, the TTS model cannot assess the information from the dialogue context, which is proved to be valuable for generating plausible and appropriate speech responses. So the current two-stage pipeline also have a fundamental difference with our understanding of human speech production process. According to a famous psycholinguist, Levelt, he thinks that the grammatical encoding and phonological encoding are done in parallel within this conceptualization, formulation, articulation process. This is what humans do when we want to speak. And inspired by this, we want to explore the possibility of building an AI speech dialogue system that thinks how to respond and thinks how to speak at the same time. So we hypothesize LLM that with hundreds of billions of parameters in comparison with BERT-based TTS frontend with only like 3 billion parameters, 0.3 billion parameters. The LLM I think it can achieve this goal. To verify this, in this paper, we provide 2 groups of experiments to demonstrate the possibility of building such an LLM-based unified speech dialogue system. We did 2 experiments. The first is a case study of prosodic structure prediction to test the speech capability of LLM. And the second one is joint prediction of dialogue response and linguistic features via LLM. So let's move on to the first case study. In this section, we want to validate whether LLMs, which have been well proved to have superior semantic understanding abilities, but are trained on the text-only corpus, can handle this speech-related task. The task is prosodic structure prediction. The prosodic structure is one of the most important linguistic features in Chinese or Mandarin TTS, and is strongly related to the syntax of the sentence. You can see this is prosodic word, prosodic phrase, and intonation phrase. It's like a tree structure. And the prosodic word is #1, #2, and #3 accordingly. In the following, we present two methods for adapting LLM to the PSP task, that is prosodic structure prediction task. The first one is prompting, and the second one is fine-tuning. And the data we utilize is Data Beaker open source Chinese standard Mandarin speech corpus, which contains 12-hour speech recordings of 10,000 sentences with an average length around 16 words per sentence. It was articulated by a single Chinese female speaker. The dataset is enriched with linguistic annotations, including character pinyin, and pinyin is the phonetic representation of the character. And the prosodic hierarchy information, as well as the phoneme level, interval, and boundary data that is stored in the text grid file. Annotations for prosodic hierarchy compress the prosodic word, prosodic phrase, just like what I said in the last slide. And we split 10,000 samples with an 8:1:1 ratio for training, validation, testing. Few short demonstrations are drawn from the 8,000 training split. And here is the prompt. As we all very familiar with, prompting is the most convenient way to adapt an instruction following LLM to new tasks. We present an overview of our proposed prompt structure for PSP on LLM, which consists of linguistic knowledge like this, the prosodic word, what is a prosodic word, and the position it may appear. And the few short demonstrations provides input and output pairs to LLM for in-context learning, and input sentence and the intervened system message explain each part to the LLM. And we test this structure on the OpenAI's Text DaVinci 002 API. And here is the result. We follow the previous work on PSP task, use F1 score as the evaluation metric. The number of few short demonstrations make a significant impact like this. 4 in-context examples lead to 20% improvements to 0 shot setting. This is the, we don't give the LLM any examples, and we gave it 4 examples. And while incorporating linguistic knowledge brings another 8 improvements. Here we gave linguistic knowledge, and this is with linguistic knowledge, and this is without. And further, when swapping random demonstrations to carefully selected high quality demonstrations, like here we gave the random examples, and this is the selected examples, we have another 3% rise. So, and we further apply different levels of linguistic knowledge. It shows that linguistic expert knowledge plays a crucial role in the prediction of the prosodic word phrase, sorry. And we hypothesize an intonational phrase. You can see that it is 61 and 78. It helps intonation phrase and prosodic phrase to approve. We hypothesize it is caused by different difficulties of #1 to #3 predictions. #1 usually appears at word boundaries, while identifying #2 and #3 is we think it's not that straightforward. So in the prompting experiment, context window length is a crucial limit. We can only give it less than 16 examples, as it prohibits the LLM from learning from more training examples, and all model parameters remain fixed and unlearnable, resulting in limited learning capacity. To address these constraints, we propose a fine-tuning of our large language model to enhance prosodic structure prediction learning from a substantially larger number of training examples, up to 8,000. We only utilize GLM-2 6B model due to the limitation of computation resources. We're applying p-tuning v2 for parameter efficient fine-tuning using the official code base 5. And all the training and testing, we used NVIDIA A100 GPU for, and previous BERT-based models regard PSP as a token classification problem, where the model needs to determine whether there is a prosodic boundary after each character and what level it is. In contrast, here we formalize PSP as a sequence-to-sequence prediction task, where input X is the raw sentence and the output Y is a string of character sequence with hashtag and notation of prosodic structure. And here is the benchmarking result in the table. It reveals that carefully crafted linguistic knowledge that is knowledge and 16 selected examples used on ChatGPT, and it reveals that carefully crafted linguistic knowledge and selected examples enable ChatGPT to outperform the traditional method. Here we can see it's 80%, 81.2, and here is 79.80. But such a prompting-based learning strategy failed at smaller open-sourced LLM like ChatGLM's 6B due to its limited instruction following ability. However, it shows that fine-tuning smaller LLM can outperform prompting larger LLM. Here, 82% 33 with 80% 1.2. Unfortunately, so last task, we can prove that LLM is capable of doing some speech-related task here, but unfortunately, the DataBeaker dataset only compromises isolated sentence recordings, and there are not any other datasets having dialogue context and parallel speech recordings or annotations. Draw inspiration from the long-form approach. We prompt ChatGPT to anticipate the dialogue context and transform it into a dataset of a single-term dialogues. That is, here we can say we have a sentence from the DataBeaker dataset. As a result, when I went to work this morning, the simulator laid here resentfully, but the husky disappeared. But it doesn't have the context. So we prompt GPT to give it a context. Please generate the most likely sentence spoken by A based on B's response. So here we can get what's going on, where did the husky go? So we transform a single sentence to a single turn dialogues from a sentence to a dialogue. And then we automatically extract the following categories, characters, their corresponding duration, pinyin, and prosodic hierarchy, and the highest and lowest pitch values. The use of D value is inspired by a linguist. And here we get all the information we need. The input is here. The input is generated by the GPT, and output is the original data we have, and all the linguistic information we extract. And then we because p-tuning failed to learn how to generate dialogue response and JSON-style linguistic features. So for this section, we turn to use full parameter fine-tuning to enable more learning capacity. We use 4-bit quantization to boost memory efficiency, as JSON-style encoding tasks takes much longer context than that in PSP task. And here is the final result. So on the unseen testing samples, the model successfully generated JSON-style linguistic features with 89.70% success rate here. And however, due to the limited capacity of small LLM, missing characters are frequently observed, and only 69% characters in ground truth can be found in generation results. We visualize the model prediction versus the ground truth of continuous values. Again, we observe that the model efficiently fits the training set and demonstrate a certain level of generalization ability when applied to new data. So here comes the conclusion. In this study, we present 2 groups of experiments to validate the possibility of building an LLM-based spoken dialogue system that thinks how to respond and thinks how to speak at the same time. In the first group of experiment, we proved that LLM is a competitive prosodic structure predictor, which means that its rich word knowledge and semantic understanding ability acquired from the text-only pre-training data transferred to benefit speech-related task. And based on this observation, we further involve many other linguistic features in our second group of experiments and further prove that it is possible for LLM to learn to generate dialogue response and speech features at the same time. And here's some discussion, and just to say one point, that it is important to know that so far this study does not include subsequent acoustic models and vocoders, and is not able to generate audio forms. So we only use speech linguistic features to represent speech information. So maybe to train a acoustic model or vocoder is my future work. And that's all. Thank you.